Welcome back to London Gold, everyone. Thank you so much for supporting the channel. In today's lesson, I'm going to be walking through a NMR spectroscopy question, clues to help us just the spectra and the molecular formula. So what I'm going to do is sort of walk you through my thought process of how to deal with a question like this and how I get to the answer using the spectra that we have and other things to think about, even though there isn't any information to go on other than just a formulae. Let's get into it. Now, these questions come at the end of the organic syllabus for A-level chemistry and advanced placement chemistry from the US. They tend to be the hardest because they rely on you knowing all of the organic content in the syllabus before you can identify the molecule. So the spectra that I will be using for my chemical shifts, I've attached below. So look at the description below this video and use that. If not, if you have your own one, please do use that. And let's start. So the proton NMR spectrum of X, C5H10O2 is shown below. And that's it. We've got to work out what compound X is. So there's two things I'm thinking of immediately before starting this question. Well, number one is this formula. This is what my head is thinking before I look at the spectra. I can see that there are two oxygens. So the first one that comes to mind is the ester, C double bond O, C single bond O. And the other one that comes to mind is the carboxylic acid, C double bond O, OH. Or it could actually be an aldehyde or a ketone with, at some point along the chain, a hydroxy group. Okay, so that's keeping in my mind as well. And then finally, we've got, it could be a carbon bonded to an oxygen, bonded to another carbon. So that is the ether group. So that was the first thing I was thinking about. The second thing I was thinking about is, well, actually rule number two, these numbers here, which are very useful. So these, they are the integration values. So when you see a little number across the top of the peak, usually it's written as like 3H, or just in this case, just 3. That tells me, for example, in this particular environment, there's 3 hydrogens. Right, so now I'm going to attempt to work out this. So I'm going to look at my data table and I'm going to look for a carboxylic acid. So a carboxylic acid that is between 11 and 12. Well, if you look at this spectra, it finishes at 5. So that means immediately I can rule out the carboxylic acid. It can't be a carboxylic acid. An aldehyde and ketone, they tend to have values, again, using my data table, between 9 and 10, but it finishes at 5. So they're out as well. So they're gone. So that leaves me with a possibility of an ester or an ether. So now I need to dig a little deeper to find out which one it could be. So for that, I'm going to start looking at the shift values. So this one here, right, that's about 1.2, 1.3. That indicates a carbon, a hydrogen attached to a carbon, which is bonded to another carbon. So it's going to be some alkyl sort of group. And the fact that it has 3 hydrogens in that environment kind of suggests probably going to be a CH3. So I'm just going to put that out there and leave that as a CH3. Now this one, this is always a really popular one in these type questions, is the one at about 2.1 and 2.2. So it has to be a hydrogen attached to a carbon to a C double bond O. It's got 3 hydrogens. It's a singlet, which means the carbon it's attached to does not have any hydrogens. So according to the n+1 rule, the number of hydrogens on the adjacent carbon is 0. So that means I can correct my drawing now, and I know that it's going to be a CH3. There has to be a CH3 there, attached to a C double bond O. Right, look at these two. So we've got 3.5, 3.6, that looks to be, and it has a 2, and I can see that it's split into a quartet. So this might be a CH2, and the fact that it's split into a quartet means it's next to a carbon which has 3 hydrogens attached. So N would be 3, 3 plus 1 makes 4, which is a quartet. So I'm using the n+1 rule here to work out the splits. A splitting pattern is caused by when you have a hydrogen environment you're considering, and then you look at the carbon next to it and the number of hydrogens on that adjacent carbon. So if you look at my little diagram here, imagine that's the environment I'm considering, right? You look at the carbon next door and you look at the hydrogens on it. There is 1, 2. So for that environment, N is 2, which means 2 plus 1 equals 3. So that particular one would be a triplet. So just going off the point there, just to explain the splitting patterns to you and how we can use them. So we know there could be a CH2 next to a CH3. And then finally, we've got this one, which is basically on 4. And the only thing that fits that is a carbon with a hydrogen attached directly onto an oxygen. But also it's a singlet. So the fact that it's a singlet means it must be next to something which doesn't have any hydrogens. And it's a 2, so it has to be a CH2. So we call this A, let's call this B, let's call this C, let's call this D. So the idea is just to work through this slowly. And as I said, I'm just thinking aloud, not knowing the answer to this. And what I like to do, like I've done in previous lessons I've taught, is just put the pieces down almost like jigsaw pieces, right? So we know there's a CH2 and it's bonded to an oxygen. And there must be something on the other side of it which doesn't have any hydrogens. How do I know this? Because it's a singlet. Then we know for B, another CH2, but that's going to have carbons either side of it with hydrogens because it's split into a quartet. So I don't know enough about that one yet. Then for C, that's a bit more obvious. We've got a CH3 bonded to a C double bond O. And then the last one is a CH3 attached to something. But I can see that that's split into a triplet, which means it must be next to a CH2. So that's a nice little indicator there. So how can I fit A, B, and C together to make this work? This can't be an ester. The reason why is because for it to be an ester, we have to have the C double bond O attached to the oxygen like this. And then we have a CH2. If we had a carbon coming off of that, that cannot, where I'm putting that line, that cannot be next to any carbons which got hydrogens. How do I know this? Because this peak here, A, is a CH2 directly attached to an oxygen. So what's going to go next to it if I can't put a hydrogen? Well, I can't just leave it blank, and it can't be another carbon because I'd have to put hydrogens on it. So the point I'm making is for this to have an integration of 2, it has to be a CH2, and it must be attached to something here where this question mark is, which doesn't have any hydrogens. So let's propose something. So we've got CH3, C double bond O. So instead of having the oxygen there, which would make the ester group, let's put that bit in instead. So that now goes here, and then we have an oxygen. And then the other side of the oxygen, we've got to put parts B and C in. B and D in. Well, we know this one is a triplet, which means a CH2 attached to a CH3. And we know that B is a quartet, which is a CH2 next to a CH3. So B and D work perfectly together. We end up with something that looks like this. So let's circle the environments. Use a different color. So that CH3 there, which is a triplet, is D. This CH2 here, which is the quartet because it's next to the CH3, so 3 plus 1 makes 4, must be B. Then we have the oxygen, and then we have, this was the difficult bit to identify, we have this other CH2, which is this one there, and that's a singlet because it's next to an oxygen on the right-hand side with no hydrogens, and then it's next to a C double bond on the other side, which doesn't have any hydrogens. So that means it's going to be a singlet. So that has to be A. And then final one, which is the C double bond O attached to CH3, which is this one. I think I called that one C. Okay. So with the molecule we have is it's a ketone with an ether group. So that was a really difficult one because most people would have fallen into the trap thinking it was an ester, but it's not. It's a ketone, C double bond O with CC either side with an ether group present. Right, if you have any questions on this one today, please comment down below and I'll get back to you. This is probably one of the hardest ones I've done, especially for an A-level paper, because if I'm honest, the ether group is just often forgot about. People, tend to get questions on benzene, aldehydes, ketones, esters and carboxylic acids, especially carboxylic acids. So for this one to come up is unusual, but I'm glad that it did, so you can see how to work out something like this.